Now, when we go back to our aspirin and LSD example, when we draw the pills, uh, it it becomes a different issue if you replace them in the box or not when drawing them. So it gives you a different approach because you will have some extra information knowing that what was the previous pill or something like this. Now, if we need to emphasize this, we can write like this. For example, let's suppose that your event A is your first pill is LSD, and your event B is your second pill is LSD. You see here. So the thing is, normally, if you replace the draws, when you draw the pills, you put them back in the box again. The thing is, your PA should be 20 over 100. Okay, but this would be exactly equal to PB as well. But this is with replacing them, okay? But without replacing them, your PA would be again 20 over 100, but your PB would be different depending on the outcome of your first draw. It can either be PB equals 19 over 99. So if that was the first pill was LSD, or it could be 20 over 99 because the first pill can be an aspirin. This is where conditional probability takes place. Namely, you can write this in this manner, which is called the conditional probability. P, you know that A happened here, so that's the idea. So your probability of B given A would be 19 over 99, where your probability, where your probability of B given not A would be what? 20 over 99. Namely, these correspond to those cases. If we look at this issue in this set theoretic view, like if we write this our sample space something like this, suppose that those are your events, namely A and B, for example, and this is where both is happening, this shaded region. So what you're doing is just limiting your sample space with respect to given information. So what I'm curious about is this one, for example, in this case. Given that A, what is the probability of B happening? It means that you are limiting your area to this one rather than your sample space, and you're curious about the shaded part here. So this is what we're talking about, and if you write it like this, for example, given B, what is the probability of A here? In this sense, again, you're talking about this intersection region. However, this time over PB, right? So it would give you the another let's say possibility here, given that B, what is the probability of A happening? It means that it is limited to this area, and you're curious about this probability. This is called the conditional probability. So good. So if we go, Okay, this is another example, and this is the sample space for throwing two fair dice. Okay, when we throw two fair dice, what happens is here, namely, okay, two fair, the outcomes of two fair dice, and so suppose that your x1 is value of the first one, and x2 is the value of the second one. Okay, second one. So let's define two events here. Event A will correspond to your x1, and x2 would be such that x1 plus x2 would be equal to 10, for example. Okay, that's the case. And your event B, this is the example from our textbook, x1 and x2 would be such that your x1 would be greater than x2, for example. So this is just a scenario. And what would be our sample space? This one, right? We will have all the possibilities here given here, our sample space, and these are our defined events. Now let's take a look at the subsets or the elements of those events particularly. If you consider, for example, set A, it would be 5, 5 and 4, 6 and what else? 6, 4, right? There can be nothing else, because if you choose anything other than this, it would be less than 10. We're curious about the or for example, if you choose 6, 6 or 6, 5, it would be above 10. So what we're trying to do here is defining the combination that gives us exactly 10 when you add them up. Okay. And if you take a look at event B, that should be, for example, the first one would be greater than the second one. Okay, it starts from this one, and all the combinations of, okay, up to here, that would be 3, 4, 5 and 6. Then you go ahead with 2. Okay, and then you go ahead with 2 here, like it would be 2, oops, 3, 2, starting from this one. Then you again increase this one like 4, 5 and 6. That's how we do it. Okay, and up to what? Finally 6, 5. Okay, that would be your B events elements. Okay, what are the probabilities of this? Probability of A would be 3 over 36, where your probability of B here is 15 over 36, if we write all of these down. What we're curious about is, what is probability of B given A? You can do it directly from this, since you have 3 possibilities here. And which is the one that larger than the first one is larger than the second one? That's one particular. It is 1 over 3, right? You first limit your sample space, because there's an information here, extra information, to 3. Then you determine which is the occurrence of B here, and vice versa. What is the probability of A given B here? You can again, here you have 15 elements here, and namely which one is where the outcome is 10. When you add them up, the sum of them is 10. If the first, remember, the first one should be larger than the, oh, no, let me check. The B is okay, there, the first one should be larger than the other one. It should be this one again. Am I right, or did I make a mistake here in the first one? Probability of given A, it's 10. Probability of B, again that one. Okay, it's 1 over 15 again. Anyway, so this is how we do it. There is another way for calculating this, if you remember from our set view here that we just discussed a few moments ago. If you think about this as a set view, so they would it can also be calculated like this. So like probability of B, A should be probability of A intersection B over probability of A. And what would that be? It is 1 over 36 over, what is the probability of A here? 3 over 36, which would give you 1 over 3 again. And your probability of A given B is, again, the intersection region over probability of B this time. And it would be 1 over 36 and over 15 over 36, which would give you 1 over 15, and they would be, of course, the same results with slightly different approaches, but it's the same. That's the idea with the conditional probability. Now, if we look at the properties of conditional probability, we can write them down as well, which are important again to make those definitions. The first one is the conditional probabilities would be again between 0 and 1, not surprisingly. Okay, and the probability of having something in sample space, if you know that A happened, it's directly 1, because you know that a subset happens, that set, larger set, directly happens. And if you assume that B1 and B2 intersection is the empty set, is the empty set. So that means that they're mutually exclusive, right? If B1 happens, you know that B2 cannot happen, and if B2 happens, B1 cannot happen. So in this sense, your probability of B1 and or B2 happening given A should correspond to the addition of them separately. Why? It comes from the addition property of our calculations, right? Because they cannot happen at the same time. Just remember our bus travel and train travel example, right? We did this a few moments ago. And if we generalize this, if you have J events like this, many events like this, BI intersection BJ equal to the empty set, where your I is not equal to J, so all combinations of this one, then it means that all of their combined probability B1, B2, B3, up to Bj, for example, given A should be all of their probabilities B1A plus probability of B2 given A plus up to probability of Bj given A. That's right. So if we try to clarify this with an example, we can refer to the example in our textbook, where they where they focus on the calculator types and colors of students in a particular school. Suppose that those calculators can be either electronic or mechanical, and they can be either black or, let's say, gray. Those are their colors, and they write the numbers of them. That's the idea. So they're 40, 20, 40, 30, 10. So if we put here their totals, from this one as well, total, and we have 60 and 40, and in this row 70 and 30, and in the end you will have what? A total of 100 calculators. Okay, now here comes the question, conditional probability question. What is the probability of, let's just write them some names. Event A, the calculator is electronic. Event M, the calculator is mechanical. Event black, the calculator is black. Event G is the calculator is gray. Okay, what is the probability of E given B? If we know that the calculator is black, what is the probability that it is also an electronic one? So you can go ahead and write this directly. So limiting the space here, it is black. Okay, 70. And what is the probability of having 40 here? 40 over 70, you see? You can do it directly like this. So it is 4 over 7. Or, as I told you, as we discussed a few moments ago, you can do it like this from set theoretic view directly. It's also, again, set view, but just another type of approach to the problem. PB. You can go ahead and solve it like this. So what if they're electronic and black at the same time? This one. What is the probability of this one? 40 over 100, right? So it is 40 over 100. Over. What is the probability of being black here? So it is 70 over 100, you see? So we write this as well, 70, 100, and the result will be again 4 over 7. Of course, they will match. That's the idea. Okay. Now, we can use conditional probability for exploring some unknown probability A using all those mutually exclusive events. Now, let me try to tell you how we address this. Okay, so suppose that they're all mutually exclusive events. Okay, those B events are all mutually exclusive. Your if, let's define them as properties. Let's write like this. First property is if BI intersection BJ is equal to the empty set where your I is not equal to J. Of course, we just discussed this in a few moments ago, right? And the second one is when you talk about all of these B events happening, it would give you, BI If you combine all of them, you will get the sample space. Look at this. Here you see, if you combine all the B events here, you will end up with the sample space. That should be another assumption. So, and the third one is your probabilities. Each of them should be larger than 0. So it means that from 1 to k. So your I is from 1 to k. So at least one element of B will happen, but mutually exclusive, of course. One of them will happen. If one of them happens, the others will not. That's the idea. Now, if we try to clarify this issue with an example, suppose that your S is sample space is from 1 to 6 for a fair die. Okay, die. You have a die here. And suppose that your B1 is 1, 2, getting those results. B2 is getting event 3 elements in that event, and your B3 event is having the remaining elements. You see, do they satisfy these conditions? Yes, exactly, yes. So this one is perfect. But what if we add more events here in this case? How can we fit them here? Your B4 is 1, 2, 4. No, it's not possible. Look at this. They're overlapping, right? So their intersection is not an empty set anymore. We cannot put them. That's the idea. Okay, and what about another event, for example? Let's say it's B5 where you have this one. So again, no, I mean it's just corresponding with this one, or this one matching with this one. No, that's not possible. So as you see, these are not satisfying those conditions. That's the idea. We're talking about cases like this. So if this is the case, and your A will be the intersections of those union A intersection B2 union up to ... A intersection B7 here. Let's go back and see if this holds. Okay, let's go back and see this. See, if this one added this one, this one, this one, and this one added together. Oh, you also add this one and this one as well, but they're 0. So you add all of them up and you will get eventually the A event. Okay, so you're like marginalizing out the A event from the known B events. It's something like this, roughly. So your PA will be, not surprisingly, PA intersection B, B1 plus PA intersection B2 plus ... up to probability of PA intersection B7. So great. And and if you take a look at this, if you write that PA given BI, if you write this like this, and PA intersection BI PBI, right? This was an equivalence that we had. If you move this one to here, what you will have here are all of them separately, right? And you can write them directly. PA given PI, and given BI will be all of the probabilities of these ones, and it would look like a probability of A, B, 1 probability of B1 plus probability of A2 probability of 2 dot 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 plus probability of A probability 2 probability of B7. Okay. So now in this sense we can say that it is A is marginalized out of those those B's. It's maybe it's a version of the fourth property given in the 36th slide of this session. Okay, let's try to give an example to clarify this useful property here. Suppose that 3 factories are producing drugs, a drug company. This is an example given, taken from the textbook again, drug company, simple one. And the factory 1's capacity is twice the capacity of factory 2 and factory 3. That's the, let's say, assumption, and they are equal. Okay, we can write it like this, I think. 3, 1 is, can I write it like this? 2F2, 2F3, okay, maybe. And the first, okay, F1 and F2 produce 2% defective rate, 2% defective rate, and your third factory produces with 4% defective rate, those drugs. Okay. Suppose that all of these 3 factories drugs are collected in a single storage area, for example, a single storeroom or something like this, and we take 1 pill from that storage. Take 1 pill from, not pill, a box, for example. Take 1 drug, for example, okay, a drug box or something like this. What is the probability that it is defective? This is what has been asked to us. So we need to define our events first. Okay, let's suppose that our first event is it is defective. Okay, and your B event is what? It is produced in factory 1, and your C event is produced in factory 2. Oops, let's name them a little properly. B2 is produced in factory 2 and B3 is produced in factory 3. So great. So what we have here is we're trying to have something like this, right? I don't know whether it is I hope I drew it correctly, hopefully. Like I'm trying to have the production capability of well, have here B1, B2. Okay, this drawing can be wrong, but I'm trying to roughly give you the idea about it. So here is your A. Okay, this is what we're trying to find out. How are we trying to find out? By trying to calculate those intersections and adding them up together to marginalize the A out of those B. What we're trying to do is something like this. So you will write your probability of A should be probability of A, if you know that B1 happened, B1, okay, plus probability of A, if you know that B2 happened, the probability of B2, plus, oops, not very good, this one, probability of B, oops, not, I'm sorry, A given B3 times probability of B3. All right, so we have all the numbers here, in fact, so we know that the F1 and F2 factories produce with 2% defective rate, and F3 factory is producing with 4% defective rate. So it means that if I'm so if it is first factory, it should be 0.2. So and if it is second factory, again 0.02, and this one should be 0.04. And I know that getting a drug from the this production company is producing twice as much of these, so it means that you need to put here like 0.25 and 0.25 and 0.5. You see, this one is twice the amount of this one. So now it looks very handsome, no problem. So when we make the necessary calculation with our calculator, the result would be something like this, which is 2.5% impact would be our answer to this question. Okay, if we return to our previous example, like the question that we first asked at the start of conditional probability. Okay, let's just say ask the same question again. We have a box of pills here. Let me just remind you the question, where you have 20 LSD and 80 aspirins in it. Is that right? Okay, in it. And what is the probability of your second pill? Okay, what is the probability of second is LSD if you don't know the outcome of the first one. Okay, that's the idea. So it means that your probability of A should be 20 over 100, and let me just write them down. Okay, this is first pill LSD, and suppose that B is second pill is LSD. Okay, the probability of A is 20 over 100, and probability of having an aspirin is, of course, the remaining one. And in this sense, probability of B given A should be what? We know this from the start. Probability of B given not A should be 20 over 19. But the question is asking you if you don't know the outcome of the first one. So it means that your probability should be marginalized out of what you have here as information. So plus probability of B given not A, probability of not A. So it's pretty straightforward, right? In two ways you can get B, you can get the second pill as LSD. Either your first draw was another LSD, this is the probability of this happening, and or it can be your first pill cannot be, your first pill can be an aspirin, and you can draw an LSD in this time. So you, when you add them up together or calculate them together, we already have them, times your probability of A is, look, we have all the components here required, and B over, I'm sorry, B given A naught, and probability of A naught is this one. So when we make the necessary calculation, look, I mean, they're coming from here, right? This one. And probability of A is coming from here, this one. And your probability of A naught is going, oops, let me choose another color. This one is going right here, and this one is right here. You see, that's the idea. When you make the necessary calculation, you will end up with what? Not surprisingly, okay, what are you expecting here? Of course, it is 20 over 100, because suppose that you're making the draws here, first, second, third, blah 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 blah, until, well, that's the idea. But for example, if you don't know what happened here, so it means that it's like you're making the first draw here, so it would be directly 20 over 100. Okay, that's all about the conditional probability.